Okay, so in 6.3, we're going to look at solving quadratics with square roots or using square roots. But before we talk about how do we solve, we're going to do a little let's review radicals. So a radical is any expression with a square root, a cube root, etc. It could be a fourth root, fifth root, whatever. Your radical symbol looks like this, right? That square root symbol. And we are going to list our first 15 perfect squares because knowing those perfect squares is going to make simplifying radicals a lot easier. So perfect squares are created when we multiply a number by itself, right? Like 1 times 1 is 1, so 1 is a perfect square. 2 times 2 is 4, so 4 is our next perfect square. And then 3 times 3 or 3 squared, so that means our next perfect square is 9. 4 times 4, so that's 16. 5 times 5, so our next perfect square is 25. Next perfect square is 36. Then 7 times 7 would be 49. And then 8 times 8 would be 64. 9 times 9, 81. Then you have 10 times 10, which is 100. Then 121. 12 times 12 is 144. Anybody know the next one? 169, very good. And then for 14, you just flip-flop. 196, very good. And then 15 times 15 is 225. So knowing your perfect squares is going to help you in this next part where we review simplifying radicals. When we're simplifying radicals, there are 2 cases here. Case number 1 is if you have a perfect square. So if you have a perfect square underneath this radical symbol, you just take the square root of that number, meaning like the square root of 4 is 2, because 2 times 2 is 4, or the square root of 9 is 3, because 3 times 3 is 9. So if you look at number 1, I have the square root of 49. 49 is a perfect square, so the square root of that is 7. Number 2, I've given you the square root of 36 over 121. Well, when we have a fraction underneath that radical sign, you're essentially just taking the square root of the numerator and the denominator. And in this case, we can simplify that because both 36 and 121 are perfect squares. So the square root of 36 is 6, and the square root of 121 is 11. So that would simplify to 6 over 11. And then for number 3, we have 2 times the square root of 9. So this problem is an example of this last little note that I have on here where it says for both cases, if there's a coefficient outside of the radical, so this is a coefficient, meaning this means 2 times the square root of 81. So we're going to multiply this coefficient by any number that we take out of the radical, all right? And in this case, we have the square root of 81. 81 is a perfect square. So what number are we going to take out of that? The square root of 81 is 9. And so we would do the 2 times 9 and get 18. Okay? Now, not every radical is going to be a perfect square. So this is where case number 2 comes in. If you do not have a perfect square underneath the radical, we're going to break that radical down using the largest perfect square that it's divisible by. Once we find that perfect square, we'll take the square root out and then leave whatever's left over underneath the radical symbol. So yes, I already heard it for this first one, but for number 4, we have the square root of 45. So if you look at your perfect squares, the largest perfect square that 45 is divisible by is 9, right? I already heard it, 9. So we'll break this down to the square root of 9 times the square root of, 45 divided by 9 leaves me with what? 5. So now that I have this perfect square under the radical, I can pull it completely out. The square root of 9 is 3, and then I'm going to leave this remainder underneath the radical symbol. So I have 3 square roots of 5. All right.
Miss Raiden, where did you get that?
Where did I get the 9? Yeah. I'm looking for the largest perfect square that 45 is divisible by. 9 is a perfect square. 45 divided by 9 is 5.
So it has to go into even number?
Yes. Okay. Yes, it has to be divisible by that number.
Oh, okay. Thank you.
So it's what is that number under the radical divisible by, not just like, well, 36.
Yeah, that's what I was saying.
No, 45 is not divisible by 36. So then now let's look at 112. And some of these might be easier than others. So a lot of times, like, you're just picking up your calculator and it's almost like a guess and check thing. You're doing 112 divided by 4, 112 divided by 9, 112 divided by 16, 112 divided by 25. You're figuring out what is that largest number that 112 is divisible by. And it is 16. Very good. So you'll break that down to the square root of 16 times the square root of 7. Because when you did 112 divided by 16, your remainder, your leftover, is 7. And again, now that we have this perfect square underneath the radical, we can take the square root of that. So the square root of 16 is 4, and then we're going to leave that remainder underneath our radical. So we have 4 square roots of 7. Ainsley, do you need to charge yours or something? And then last one to practice here, number 6. We've got 5 times the square root of 72. So again, now we have this coefficient. So what this means is just whatever we can pull out of the radical will have to be multiplied by the 5. Okay? So first, let's focus on seeing if we can simplify the square root of 72. So again, if you need to, you're using that calculator to guess and check. 72 divided by 4, 72 divided by 9, 72 divided by 16, 72 divided by 25. Very good. 72 is divisible by 36. So we'll break this down to the square root of 36 times the square root of 2. And then again, we still have that coefficient out front. Now that we have this perfect square, we can completely pull it out of the radical. So the square root of 36 is 6. So I'm left with 5 times 6 square roots of 2. Multiply these coefficients. 5 times 6 is 30. So I have 30 square roots of 2. So it's going to be important that we feel comfortable simplifying radicals if we are solving using square roots. We got to be able to simplify square roots. And that's what we're going to move into next. So when we're solving quadratics by square roots, this method works if your quadratic looks one of 2 ways. So this works if there's no bx term. So if there is no middle term in your quadratic, then you should solve using square roots. Or if your quadratic is in vertex form. So if there's no bx term, or if your quadratic is in vertex form, it's going to be quickest if you are solving this using the square root method, okay, using square roots. So filling in what this property says, or what this, yes. If a quadratic equation can be written in the form x squared equals n, whatever that numerical value is, then the quadratic can be solved using the square root property, which says if x squared equals n, then x must equal the positive or negative root of n. So the positive or negative square root of n. So keep in mind that even though in these first ones that we practiced, 1 through 6, we only gave like the principal square root, which is the positive square root, because that's the most common. But every square root actually has two roots, the positive and the negative. Because 7 squared is 49, but also negative 7 squared is a positive 49, because a negative times a negative is a positive. So every root has going to have two, the positive and negative solutions. So how do we solve in this, or using this property? The first thing you're going to want to do, step number 1, is rewrite the equation so that you have x to the second power, x squared is equal to n. So we're going to isolate x squared. We can go ahead and do step number 2, which is to take the square root of both sides. And then step 3, this last step, is to simplify that radical on the right side, making sure, like we just talked about, that you have plus or minus to indicate both answers. So first, if we look at problem number 7, we've got x squared minus 64 equals 0. So again, the first thing you want to do is get x squared all by itself on the left side. So I'm going to bring this negative 64 over to the right. So this would become x squared is equal to 64. And now that we have the x squared all by itself, because the inverse operation of squaring something is to take the square root. So we're essentially just using inverse operations here. So we square root both sides, because again, the square root is going to cancel out the square, so that I'm just left with x. In the case of number 7, 64 is a perfect square. What's the square root of 64? So the answer is x equals plus or minus 8. You have two answers, positive 8 and negative 8. All right. Number 8, 81x squared plus 5 equals 21. So again, if we're going to use that square root method, which we can do because there's no like x to the first, there's no bx term, but I need to isolate x squared. So I'm going to use inverse operations just like you would with any type of equation where it says I need to move over the constant first and then the coefficient. So the first thing I'm going to do is subtract the 5. So that I have 81x squared is equal to 16. And then all I have to do to get x squared by itself is get rid of the coefficient. Since it's being multiplied by 81, I'll divide. Which means x squared equals 16 over 81. Now that I have the x squared isolated, now I can go ahead and take that square root. And luckily for us, these are both perfect squares. So your answer becomes plus or minus. Do not forget, there's two solutions. 4 over 9. Plus or minus 4 over 9. All right. Moving on to number 9. We have x squared plus 1 equals 17. So again, we need to get x squared by itself. So just like every other time we solve an equation, move the constant over, then move the coefficient. So we subtract the 1. 8x squared is equal to 16. Then we will divide by the 8. So that leaves me with x squared is equal to 2. And now that I've isolated the x squared, I can go ahead and take the square root. Because the root cancels out the exponent. So x is equal to, is 2 a perfect square? Is it divisible by any perfect square other than 1? No. So we get to just leave this as plus or minus the square root of 2. If you can't simplify the radical just stays there, okay? So you could have a radical in your final answer if it cannot be simplified. So x equals plus or minus the square root of 2. All right, one more that looks like this form where it's got no bx term. Yours says 50 right here, which is what we want. So again, we're isolating the x squared first, so move over the constant, then move over the coefficient. So we're adding the 4. 2x squared equals 54. Now we're going to divide by 2. And we get x squared is equal to 27. My last step here is to now take the square root to get x by itself. When I go to simplify this radical, it's not perfect, but we can break it down, right? Because it is divisible by a perfect square. Which perfect square is it divisible by? 9. Very good. So the square root of 9 times the square root of 3. I knew it. So fun. Yay. Congrats, guys. Okay, so now that we've broken down the square root of 27, we can take the square root of 9. The square root of 9 is going to be 3. So x equals plus or minus 3, and then that leftover square root of 3. So x equals plus or minus 3 square roots of 3. All right, our last two look a little different because these now look like vertex form. So when we are simplifying them in vertex form, it's a little different because if you think about just order of operations like we were talking about, we would undo whatever's in parentheses last. So this time we're going to go ahead and take the square root of both sides first. Okay, refocus. We had our time. Now it's back to focus. So we've taken that square root, so I'm left with now just what's in the grouping symbol. X plus 2 equals, the square root of 49 is perfect, so positive and negative 7. So now, all I have to do to get x by itself is subtract the 2, but when you subtract the 2, you have to subtract it from the positive and the negative root. That's how you get those two answers. So 7 minus 2 is 5, and then you would do the negative 7 minus 2 and get negative 9. So those are your two solutions for that quadratic. And then our last one on our notes here, number 12. Again, this looks more like vertex form. So we're just thinking PEMDAS backwards. So this one has a coefficient. All of this is being multiplied by negative 2. So let's undo the multiplication. Then we'll undo the exponent. Then we'll undo the grouping. Exactly. So we're going to divide by the negative 2 so that cancels that out. Then we've got x plus 7 squared is equal to 20. Now we can do the inverse of squaring something, which is taking the square root. So that I'm just left with what's inside the grouping symbol, which is x plus 7. 20 is not a perfect square, but we can simplify it because it's divisible by what? 4. So we can break this down into the square root of 4 times the square root of 5. Now that we have the perfect square, take the square root of it, which is 2. So this becomes plus or minus 2, and then that leftover square root of 5. Now, all I have left to do is bring the 7 over to the other side. So we'll subtract the 7 from both sides. Are these like terms? Look at my head. No, they are not like terms. So you cannot combine them. So you're just going to rewrite this as negative 7 plus or minus 2 square roots of 5. So that's how you'd still have two solutions, because it'd be negative 7 plus 2 square roots of 5 and negative 7 minus 2 square roots of 5. Okay, so you still have two x-intercepts there.